So our third example problem to wrap up this unit of study comes from the AP Level C exam. This is from the year 1980, and we're told there's a thin plastic rod with a uniform, this is going to be important, a uniform linear charge density expressed as lambda. This rod is bent into a semicircle, and we have to determine the electric potential at the origin. Well, I'll give you a chance to print out this document and grab a calculator if you need it. Actually, I don't think we're going to need a calculator on this problem because no numerical values are given. Everything's going to be expressed in terms of variables. So print the document and then unpause and resume this video once you're ready to proceed. Okay, so hopefully you've read through the entire problem now. Let's take it from the top. Determine the electric potential at the center of curvature of this bent rod. Put in an x-axis and our y-axis. And then imagine breaking this total charge up into a bunch of little bits dq. Okay, so let's focus on this one right here. There's a little bit of electric potential at the origin due to that little bit of charge, and this would simply be equal to k dq divided by capital R. So to get the total electric potential of the origin, we need to add up the contribution from every element of charge. So we just need to integrate k dq over r. So this is capital R, not lowercase r, it's a constant. So k and r come out of the integral, and we're left with integrating dq. And we really don't even need to think about limits of integration. Regardless, the integral of dq just gives us all of the charge q. So that couldn't be any easier. The electric potential of the origin is kq over r. Indicate the direction of the electric field at the origin. Well, we've been through this problem before. We know it's going to point straight down. That has to do with the symmetry, right? So if we need to explain our reasoning, if we picture this orange dq right here, then it's got a mirror image, purple dq over here, so that the horizontal components to the electric field from each of these cancel each other out, but their vertical components add up, so the net electric field is going to point downward. Now we actually have to calculate what is that electric field. So because we're just taking the vertical components, if this is at an angle of theta relative to the x-axis, then that angle theta is also here. So these vertical components to the electric field, we'll say the net E along the y-axis is going to be equal to E sine theta. So that's what we need to sum up, right? The total electric field is the integral of all of the individual components, or all the little contributions, and only their vertical components. So in other words, this is the integral of dE sine theta, where of course dE is k dq over r squared. So the k and the r squared come out of the integral, and we're left integrating dq sine theta. Now there's two variables, q and theta, so we need to relate the two. So we can say dq is the same thing as lambda ds. That's where it's important that we noted that this is a uniform charge density lambda. And as we work our way around the perimeter, any displacement along the arc length is equal to theta times r. So ds is r d theta. So we have lambda k over capital R squared times the integral of r sine theta d theta. And then that r cancels with one of those. So E is equal to lambda k over r times the integral of sine theta d theta. And we'll double the result as long as we integrate from 0 degrees up to 90 degrees, right? So the first dq we have to account for is at theta equals 0, and then if we stop halfway through the derivation at theta equals 90 degrees, that's why we can double the result. The integral of sine is cosine. Cosine of 90 degrees is 0. Cosine of 0 degrees is 1. So we just end up getting E equals 2k lambda over r. Lastly, we need to write some sort of expression in terms of Q, V naught, and E naught for the amount of work that would be required to bring a positive point charge from infinitely far away to point P, noting that point P is located a very small distance s away from the origin as shown in this diagram. Okay, so what we're told is we've got a charge that starts really far away, right? This charge Q is initially infinitely far away on the y-axis, and then we bring it here to point P. Well, we know that the electric potential infinitely far away is 0 unless otherwise stated, and we've also found that the electric potential at the origin, V naught, is equal to kq over capital R. So if this problem was asking us how much work is done to bring this charge q from infinitely far away to the origin, our answer would just be kq over r. But we didn't bring it all the way to the origin. We brought it just a little bit short of there, right? And so as long as the distance s is really small, right, if s is much, much less than the radius of curvature, then we can approximate that over this distance that E is very nearly uniform. Of course, overall, right, broad scale, over all of space, the electric field is not uniform. But over just this little distance, we can approximate it as uniform. And so we just need to subtract. Off here we need to say that the amount of work, the amount of work is equal to Q times delta V, which means the work is Q times kq over r minus just a little bit of potential difference between points P and O. And what would that be? Well, that would just be E naught times S. Yeah, so that's all. Our answer to part D, the work is equal to the amount of charge we're moving times kq over r minus E naught S. And we've answered in terms of all the variables. Oh no, actually, we don't even need to use this kq over r. We can just call that V naught. My bad. So the work is equal to Q times V naught minus E naught S. All right.